this portion. Okay, so this is the key. This is posted online. You know, sometimes I've done the video keys. This time I just have a paper key. Sorry about the date there, right? That's, I take the old versions and change them around sometimes and forget to change the dates. So a number of students here missed this undefined value, right? So when you're finding the absolute extrema on a closed interval, you're looking for critical points, and a lot of people successfully took the derivative and solved and found x equal 2, which is a critical point, but they did not find x equals 0, which is also a critical point, right? X equals 0 makes this denominator 0, so it means that derivative there is undefined at that point, and that means that that's a critical point, right? The function is defined at 0, but the derivative is not defined at 0. So when we're testing, you can test these values, right? But you need to test both the endpoints and both the critical points. It turns out 0 didn't generate a minimum or a maximum, but it is still a critical point that you need to test. It could sometimes. The other thing is that some people, I think, were interpreting extrema to be like the max, but it actually means absolute max and absolute minimum, right? So you need to find both of those values. In number 2 here, this is the graph of the derivative, and I put it in bold and tried to emphasize that, but I think some people were still interpreting this as the graph of f. This is not f, this is the derivative. So when you're asked these kinds of questions, and I will warn you, I kind of like these kinds of questions, you want to rephrase them. So if I ask, where is f decreasing, you should know that the function is decreasing where the derivative is negative. That's how we connect those two. And the derivative is negative, we can see right here, right, over those x values and over those x values, right? So this should have been your estimate in here. Where does it have a relative maximum? We know from the first derivative test that a relative maximum goes from where the derivative is positive to negative, right? That's where the function goes increasing to decreasing. So we can see positive to negative happens here and here. And then finally, where's it concave up, right? It's concave up where the second derivative is positive, which means the derivative is increasing. So remember the relationship there, right? The second derivative is positive means the first derivative is increasing. Where this function is increasing is right from there to there and there to there, right? So those are the x values we're looking for. The other issue that came up, so this one, right, you got to be careful about what it means to be differentiable, right? The derivative has to exist. In this case, the derivative doesn't exist on that interval. Finally here, a lot of people take the derivatives and factor and find these critical numbers and then not really show me that they were doing any kind of testing of those critical numbers. Sometimes they got the right answer, sometimes they didn't. It's important that you are showing that you are doing a test there, right? Without that test, you don't know how the critical numbers impact the increasing and decreasing of the function. It may or may not be changing signs at those critical numbers. And we also need that, of course, when we do the relative extrema in part B. If you know the information here from the critical numbers, right, you know that it goes from decreasing to increasing and then increasing again and then decreasing, right? So like that's a really rough graph of the function. And so that tells me that I have a relative minimum there and a relative maximum there, right? And the same thing here with the second derivative. You've got to show that you're testing them, and there's different ways to show that and do that testing. That you can't just sort of come up with the answers here. Again, a lot of people sort of did this work, but then came up with all kinds of different intervals, and it wasn't clear to me that they were always testing those, right? So I want to see that you're doing those tests. Any questions on that key take-home work? Okay. How about anything from the homework? Any problems from the homework that you'd like me to go over?
I suppose I have a question.
Yeah.
Yeah, so I was just doing the 4.8, 4.9 homework before I joined.
Yeah.
And the very first problem, like I got through all the other not mean value, the Newton's method problems perfectly
Okay.
fine, but for some reason I can't figure out what the answer should be.
Okay. Let's talk through that one. So yeah, 4.8 and 4.9 are in some ways they would probably feel separate from the other problems in section 4, in that they are using the derivative to tell us information about the function, but they're different types of information and not really connected to this idea of minimums and maximums. So sometimes that's nice because you get a little bit of a fresh start. So here the question was this: find Newton's method with the specified initial approximation to find x3, the third approximation to the root of the given equation. So it maybe sounds complicated, but it's actually it's not quite as bad as it seems, I would argue. Let me share. Give me a second here. There we go. Okay. So Newton's method, what it is it's a strategy for finding the roots of a function. So a function, right? A root is an x-intercept, or a spot where the function equals 0. And sometimes they're easy to find, right, if you can factor the function. But if you have a complicated function, it turns out this precise location can be very difficult to find. And yet it's very important for us, because without those roots, if this function were a derivative, we need the roots or the critical numbers, right? So we need to know what these are. If we can't solve them algebraically, then we need a good approximation for them. And that's what Newton's method is. And the way it works is it says, if I want to start with some initial guess, and we call that initial guess x1, typically, or it could sometimes be x sub 0, but we'll just start with x sub 1 because that's the way they formulate it in this problem you're asking about. So clearly here, x sub 1 is not actually the root, right? I would like my x sub 1 to be as close as possible, but it's easier to draw it if I have a little space, right? So x sub 1, f of x sub 1 is actually up here. Right now I want f of x sub 1 to be 0. So I'm definitely off. And what Newton's method does is it says, if I draw the tangent line here, and notice where that tangent line crosses the x-axis, it turns out that, as given certain conditions, which are that the function is not flat or doing lots of oscillations right around this 0, this x-intercept of the tangent line, which we're going to call x2, is closer than our initial approximation. So I've gotten a better approximation here. And if I repeat that process again, I find, this is f of x2, and I find the tangent line there, we get a third approximation, x3, and it turns out that's quite a bit closer than x1 or x2. And this converges, it gets very close to the true zero, actually very quickly. It's a pretty efficient method for approximating the zeros. Now, algebraically, how we do that is we look at the equation of this tangent line. Let's call it y equals the slope. So that's f prime of x1 times x minus x1. You'd often have this on the other side, but we put it over here, right? Y minus y1, so I just add it over. So this is the equation of the tangent line, right? Slope and a point. And what we want, though, is not the equation of the tangent line, but we want the x-intercept. So the x-intercept happens when the y value is 0. And when y that value is 0, the x value is this, and we're going to call that x2. So what you do is now we want to solve for x2, and you move this over, this piece over to the other side, and divide by f prime of x1. And then you add the x1 over, and you get this formula. x1 minus f of x1 over f prime of x1 equals x2. And you suppose you could come up with that if you had to, but I think that'd be challenging, so you should probably memorize that or write that down or keep that in your notes somewhere. This is the formula for Newton's method, and what it's telling us is how to find the next approximation from the previous approximation, right? And then you could just replace x1 with x2, and then you'd get x3, and et cetera, et cetera. So, depending on what my function is, what's the function? 1/3 x cubed plus 1/2 x squared plus 12 equals 0. And my first guess, they're telling me my first guess is -3. Now, if I didn't know a starting guess, I just have to pick something that made this function relatively close to 0, right? As close to 0 as I can get will make it go faster. You can check and see what this gives us. I don't know how close to 0 it is. F of -3, we'll need this eventually. So -3 cubed, this is going to be a -9 plus 9/2 plus 12. That's 3 plus 9/2, which is 15/2, which is not really all that close to 0, right? I mean, it's over 7, but it's a starting point, and that's what they tell us to start with. So I need to figure out these, right? I just found f of x1. I need f prime of x1 too. So x squared plus x. It's relatively nice. F prime of -3 is going to be 9 minus 3, which is 6. So in order to figure out what x2 is, I take -3, and then I take minus 15/2 divided by 6. And these are calculator questions. There's no need to do these by hand. You're not gaining anything by trying to do the calculations. But what do you get? -3 minus 5/4, which is what? Minus 17/4. So 4 and a quarter. So in theory, when I plug this value of x2 into my function, I should get a value that's closer to 0, right? I'm imagining that I'm getting something here, right? F of x2 theoretically should be closer to 0 than f of x1. All right, that's our goal here. And what you would do then in problem 1 is you just repeat the same process with this. But this number now is x2, and that would tell you x3. And you could keep doing that as often as you like. It will begin to converge, in the digits won't change very much because it will be quite close to the actual value. So that's what they're looking for you to do. I will warn you that it doesn't work 100% of the time because it is a numerical method and there are some kind of like potential problems. For instance, if you have a function that looks like this and you're trying to find this x-intercept, if the function is flat right around there and you make a guess over here, all of a sudden your tangent lines could sort of shoot and start to give you approximations that are farther away, and you could end up kind of diverging. So you have to, excuse me, you have to sort of take the information and look at what's happening with it. You can't kind of blindly charge ahead with these. I mean, you probably can in these questions because they're not going to necessarily trick you with these, but in the real world, as such that it is, this will not always converge. There are some issues that can arise. So if your values, when you're plugging in these f values, if this number is getting bigger and bigger, then you should say, something's not working, right? And we might have to look at why that's not working. Any questions about that process? These questions are a little bit more superficial maybe than some of our other questions, in that there's not a lot of varieties or other types of questions that I can ask. It's pretty much this, right? Use Newton's method. So, and once you understand how the process works, you could use Newton's method 100 times if you had to. It'd be a very boring waste of an afternoon, right? But you could do it. So, normally we just want you to do kind of 2 or 3 iterations, and that'll be enough. And like I said, just use your calculator or a calculator on these and find the decimal and use that as an approximation. Other questions from the homework at all? Whether this section or the previous section?
I like to ask one thing.
Yeah.
I like to know like inflection points and the domain doesn't exist, that kind of function.
Yeah, like
like in the lab, like example in the lab, like the domain, the function doesn't exist in 0 and 5, and what will happen with the inflection point? I have to test every single intervals or that.
Yeah, so where the function fails to exist, so the question is a good one, like this sort of this edge case, like, okay, I understand critical points and things, but what about where the function doesn't exist? Because those don't count as critical points, but they do still impact whether the function is increasing or decreasing, and the same thing is true with concavity. So a function, if it doesn't exist on the function, it can't be an inflection point, because an inflection point has to be actually a point on the function. But it still could be a spot where the inflection changes. So I think it's sort of easiest to see that maybe visually. And with inflection, a lot of points, it's sort of easier to see it as an asymptote. So here's an example. Let's say I have a function. It looks like this. Okay. So if I took its second derivative, I would find that its second derivative is 0 here, at x equals 0, and at this x value. Okay. And if I checked the concavity, or the sign of the second derivative, I would find on this interval it was negative. And then between 0 and this number, I would find it was positive. Right? And then between this number and infinity, I would find it as negative. So if I wasn't paying attention, I might think, let's just say, just for something to define it as, that's 3. I might think that 0 and 3 are inflection points. But 3 is not an inflection point because it's not even a point on the graph. Now, if I asked you where's the function concave up, well, then certainly 3 plays a role in that, right? Because 3 is a spot where the function changes from concave up to concave down. So we have to pay attention to that value, even if it doesn't count as an inflection point. And the same thing holds true with increasing, decreasing. The function could change from increasing to decreasing here, but it can't have a relative min or max because the function doesn't exist at 3. Does that help?
Yes. Yeah.
Okay.
Yeah. So we need to still check, but there is no inflection points at that place, but we still need to pay attention.
That's exactly right. So like when you're
Yeah.
coming up with your intervals, you need to treat 3 just like an actual critical point, right? Or potential inflection point.
Sure.
But in your final answer, we wouldn't say that it is an inflection point.
Sure.
And you definitely can't ignore it, because if you ignore it, then you're missing a spot where the inflection might change, and it could mess up some of your other answers later on. Like if you have another inflection point over here and you don't consider 3, you might think, oh, it's concave up everywhere in here, but it's not, right? So so yes, just like you said, you have to consider it, and it's both for increasing, decreasing, and relative maximum, and concavity and inflection points. They are really the same. You run into the same issues.
Thank you so much.
Oh yeah, excellent question. Any other questions about this is very much the kind of relationship or thinking that is important, that we want to be able to know what the derivatives are telling us about the function, and that means also knowing kind of what they don't tell us too, right? We don't know everything, but they do tell us a lot, but we have to interpret it properly. And just a reminder for those of you who are maybe finishing up with the lab, your goal is to use the graphs instead of the test intervals. So rather than trying to come up with these sort of extensive test intervals, it's easiest actually to just graph what the second derivative actually is. And from the graph, it's very easy to see where something is positive and negative. We don't do that normally because graphing for us is hard to do by hand, right? We don't always know what these graphs look like, but Computer's very good at graphing, so we want to use that tool to replace our sign chart, right? And just like before, we're sort of comparing the algebra and the graph. We want to make sure that the things we're finding algebraically are matching up with the things that we are seeing graphically. And that's when we are sort of at our best as mathematicians, when we can combine those two together. If we rely completely on algebra, it can be very hard to see what our results mean and understand them. And if we rely completely on graphs, it is easy for us to miss things and not have accurate values, right? So that we're sort of the best when we combine both of those together. So that's part of the idea within the lab.
I have a question on the lab as well.
Yeah.
When we're finding relative extrema and we don't have the original function to go off of, would we with like a strategy that I thought of, I don't know if this is like correct, would be like looking at the intervals themselves and then like looking at the graph and seeing where like it's the lowest or it's the highest. Like how would I go about that?
Well, you have to be careful about the graph because you don't have the original function. So the only graph that you have is the graph of the derivative. And that does tell us about the original function, but it doesn't tell us by the lowest and highest values. It tells us where it changes from positive to negative. So remember that the critical values are where the derivative is 0 or undefined. And those critical values are relative maximums or minimums when the first derivative changes sign. So if the first derivative changes from positive to negative, that tells me my function is changing from increasing to decreasing, which is going to give me a minimum.
That makes sense. Yep.
So it's really doing what's called the first derivative test for the critical points. But what you touched on there is really important. And it came up in that take-home work as well, that when you're looking at the graph of the derivative, don't mistake that for the graph of the function, right? It's telling us stuff about the function, but the graphs do not look the same, and we have to interpret them differently. The same holds for the second derivative, right? The graph tells us some important information, but it's really about just positive and negative. So when is it above the x-axis and when is it below? Okay. Other questions? It's good. I like questions. Okay. So you guys would have completed the optimization already, which is the 4.7, I think. This is often a bit of a challenging topic or subject for students. So I just want to talk kind of big picture what we're trying to do with optimization. Optimization is finding the smallest or the biggest or the cheapest or the fastest, right? And these are obviously really important things, right? If you're running a company or designing some travel or engineering a canal to carry giant container ships, right? You are interested in these optimal values, right? What is the fastest way to move things? And all of those are questions of optimization. And so the basic idea is just that if I have a function, any function, right? Who knows what it looks at? Typically with an application, I'm only interested in the function over certain values, right? I mean, typically I don't, whatever these inputs are, whether it's units or whatnot, I can't have negative values typically, and maybe there's some, you know, upper limit on how many things I could possibly use, right? So there's some usual domain or restricted domain, and within that domain, I would really like to know, you know, what is this minimum value or this maximum value, right? Depending on what the question is, right? If it's cheapest and this is price, then I want this value, right? If it's you know, profit, then I want this value, right? So mins or maxes, but we can see that those occur at these critical values, right? Or, you know, they could also potentially occur at these endpoints. We don't always have a closed interval, but sometimes. And so this is really just a question that you've been working on in chapter 4 already. There's nothing new there, right? Find the absolute maximum. You just find the critical values and you test them compared with the endpoints, right? Or you test to see if this is a relative max or relative min. We have all of those abstractly previously. 4.7 is where we bring them into some more concrete, some actual examples. And the problem is that usually you're not given directly a function. Usually you have some sort of other relationships. And so the work in optimization is usually figuring out and writing this, which is called our primary equation. So for instance, if I want to find the cheapest, then what I want to do is I want to minimize the cost function. So what I want is a function that gives me cost as a single variable. Now, a lot of times when you get started, the cost might depend on 2 or 3 different things. And so we often need some secondary equations to substitute in so that this is just a single variable. It doesn't matter if it's X or Y or Q or whatever it is, it just needs to be connected to one single variable. And then once I have that, right, I can look at this function just as a function, right? Once I connect it to this function notation, then the sort of confusing application part drops away and I can analyze it as pure math relationship, right? And we find the critical values and we test, right? And we come up with a conclusion. Right? And I guess I should also put in their domain. We often need to figure out what the domain is so we can frame our work. And that's really like all this stuff is like the old stuff. It's just the stuff you were doing in 4.2, well, 4.3. So the new part is just making sure that you set up your problem properly, that you have a function for whatever it is you're trying to maximize. If it says find the shortest, then we would want the distance function, right? Because I want to minimize it. If it says the, you know, largest area, then I would want the area function and I would want to maximize it. Right? So the question will tell you what your function is, and your job then is to come up with that as a single variable so that you can solve it. Okay. So again, just kind of a general big picture of what you wanted to do with those problems. Okay, so we have, I also wanted to get you started here on 4.9. So these, let me just verify here. Yes, I mean, this is, yeah, this is like technically our next section, right? 4.2. I know the sections aren't really that critical, right? They kind of blend together, but so this is due on Friday. Just make sure I got that right. Yep, on Friday. So, you know, you can finish up your lab kind of today and tomorrow and then get started on this 4.8, 4.9. So we talked about 4.8, which is the Newton's method. 4.9 is the antiderivative. Okay, so it's introducing the idea of the antiderivative. And if you are good at derivatives, you will find the antiderivative relatively straightforward. It's just reversing the process, right? So we've thought of having a function and then the derivative somehow being like a reduced form of the function. It's not always reduced. I mean, sometimes it's more complicated than you got started with. And then you can take the derivative again, and maybe that's just me that sort of likes to organize it by level, but I think that's useful. The antiderivative is just moving your way back up, right, to where the function came from. So notationally, we say capital F of x is an antiderivative of little f of x if the derivative with respect to x of that function equals f of x. So we define the antiderivative in terms of the derivative, right? We just say it is the antiderivative if when you take the derivative of it, you get back what you started, right? So if I'm imagining little f as my basic function, the antiderivative is above it, and if I take the derivative of that, I should get right back to f, right? They should sort of undo each other. But you may notice that it is an antiderivative, right? So it's not the antiderivative. It turns out there are several, well, infinitely many antiderivatives. However, all of these antiderivatives are the same except for a constant. So if f of x and g of x are both antiderivatives of some function f of x, then capital F of x equals capital G of x plus c, where that's a constant. So what that says, that's actually kind of important. It says that there's lots of different antiderivatives, but fundamentally they're really all the same function, right? All of these functions that are antiderivatives are all the same except for a constant. There's no like, it's not like one antiderivative could be sine of x and another antiderivative could be like e to the x, x to the 15th or something else, and they would both have the same derivative. That can't happen. So the only way you can have two functions that are antiderivatives are that they both have to be fundamentally the same function. And you can see as soon as you get into this, you'll be able to see why the constant matters. For instance, if I say f of x equals x, then what is an antiderivative of x? Right? What is an antiderivative of this function? In other words, it's like a little puzzle. Like, what's a function when I take its derivative gets me x? And you know, I think it's a little bit of trial and error too. I think some people might try x squared right away, and say, okay, it's x squared, but oh wait, what happens if I take the derivative here? I'm going to actually get 2x and not x. So I don't want that extra 2 here. Well, I can multiply or divide by a constant, and that's not going to change this fundamentally. Now, when I take the derivative, the 2's cancel, and I would get just x. So notice that's like a little bit of a kind of trial and error approach to antiderivatives, right? I mean, it's I'm adjusting it as I need to make it work out. Now, this function, though, is not unique, because I could also have x squared divided by 2 plus 1, or x squared plus 2, x squared over 2 plus 15, or x squared plus over 2 plus 150, right? Or whatever number I want here, and I take its derivative, it's still going to get me back to x. And you're exactly right, it is the reverse power rule, because that is what an antiderivative is it's the reverse of the derivative. So all we're doing is sort of, we've been going in one direction for so long, but it turns out we can actually go back the other direction too. And all of our derivative rules can be reversed to become antiderivative rules. Okay? But the constant will never be able to sort of determine directly, because when you take the derivative, the constant goes away. So all of these different versions of this function all look the same after I take the derivative. So what we often do in these cases is we're going to write this as just x squared over 2 plus c. And this is called the general antiderivative. Right? If I don't write the c there, then I'm kind of like restricting what's going on, right? If I don't write the c, then I'm saying the function is actually this, x squared over 2 plus 150, but I don't actually know that. It could be any constant. So I want to keep that constant kind of free to move or change or adjust. So it is considered proper to write out your antiderivative as this, x squared over 2 plus c. And getting back to that idea of the power rule, we thought of this. The derivative with respect to x of x to the n was n x to the n minus 1. If you reverse this rule, what you do is you add 1 to the exponent, so n minus 1 would go to n, so that becomes, written sort of in forward direction. I start with n, so I'm going to add 1 to the exponent, and then rather than multiplying by n, I need to divide by n plus 1. So this is a rule and an antiderivative rule that is just the reverse of the derivative rule. All right, so here I was really like x to the 1, and that became x squared over 2 plus c. This works for n not equal to negative 1, because then I'd be divided by 0, and that wouldn't make sense. What happens if n is minus 1? What if g of x equals x to the minus 1? What's the antiderivative? You'd be tempted to use this rule, right? But as soon as you add 1, you get 0, and then you can't divide by 0. That's undefined. Maybe it's easier if I write it as 1 over x, right? That's x to the minus 1. What's its antiderivative? So what function, when I take its derivative, gives me 1 over x? It's the natural log function plus c. So again, that comes because of our experience with antiderivatives, right? There's nothing else there. I'm sorry, our experience with derivatives. There's nothing else there. There's no sort of deep thinking about what the function is. It's just, oh, I recognize that derivative from when I was doing these derivative rules, right? That 1 over x was the derivative of something. Turns out that something, right, is the natural log of x. We need the absolute values there to match up the domains. So maybe you're thinking, oh, I just had natural log of x. It's okay, but natural log needs to be defined for all x except 0. So I need the absolute values there. You know a lot of these other antiderivatives too. So these are antiderivatives. What's the antiderivative of sine? So this is where you'd be a little, this is where you, I guess my hope would be you'd say, oh, that's cosine. But then you'd say, wait a second, when I take the derivative of cosine, I don't quite get sine, right? The derivative of cosine is negative sine. So let's adjust it, right, and make sure it works. And then let's also remember our constant, our plus c. I think of it actually similarly to factoring. When I teach factoring, it's kind of the same idea. We learn to factor, which is reversing multiplication. It's a little counterintuitive, and it is better or important for us to check our work in the beginning so that we make sure it really works, right? So this is the factoring direction, and this is the multiplying direction, right? It's easier to take the derivative and make sure this really works. Once we do that, then we feel confident that we've got the correct antiderivative form. You know, and some of these are just, again, we just want to recognize that that's the derivative of what is secant squared, right? The derivative of tangent is secant squared. So we don't have rules for everything yet. Like tangent, we don't actually know its antiderivative yet, because that's not a derivative that we know. None of our functions have a derivative that's tangent. So it's got to be something else, and we'll learn to figure some of those out, but we don't know that one yet. There's a whole list in your book, but I did want to make mention especially of this one. Do you remember the function whose derivative is 1 over 1 plus x squared? That's arctangent. That's one that we haven't seen that much in terms of its derivative, but this function turns out to appear quite a bit, and so we want to remember that one because we may have forgotten. Again, there's lots of others. Some are easier, right? E to the x is just e to the x plus c. We will learn some better rules, or we will get better at some rules as we move through chapter 5. But it turns out derivatives are actually harder, or sorry, antiderivatives are I would say harder than derivatives. They are more of a like an art form. So derivatives are very formulaic. If you do the right rules, you get the right answer. Nothing to it. I mean, there is, we know, but it can be mechanical. But antiderivatives, some questions are really hard that look easy, and vice versa. And there's some that we can't find. We don't know how to find. So it is more subtle. In the beginning, we don't have any product rules or chain rules or any quotient rules. Anything like that is going to create a lot of problems with our antiderivatives. We'll learn some rules this course. The rest of the rules, you'll have to wait till Calc 2. And there's a lot of, the first part of Calc 2 is just a bunch of different strategies to figure out how to do and figure out these antiderivatives. We don't know quite yet why we're doing antiderivatives. We'll learn that in chapter 5. It turns out they are important to us in the same type of way that derivatives are important. They allow us to solve certain problems that we couldn't solve otherwise. So here's an example. Let me let f of x equal x cubed plus the square root of x over x. And I want you to find the most general antiderivative. Well, you have to be careful. Maybe I say that too often. That's what I say to my kids too, right? Be careful. I don't know what they're supposed to take out of that, right? It's maybe like a waiver. Like, I'm just saying, I told you to be careful, right? But what I mean is that we only know how to take very few antiderivatives. So there's often a sort of false confidence, right, in the beginning, like, oh, well, okay, I'll just charge ahead. But we only know how to do sort of these very limited things where I know directly what the derivative is, and I don't know any function whose derivative looks exactly like this. So I cannot take the sort of antiderivative of the top and the bottom separately, because that's not how derivatives work either, right? A quotient is a quotient rule, and so it would be a very complicated derivative if I kept it kind of as a quotient. So what I have to do here, and this is what we did in the beginning of derivatives too, is I want to simplify this. I want to turn this into something nicer so that I can take the antiderivative in sections or parts. So if I divide that by x, I get x squared, and then the square root of x divided by x is x to the minus 1/2, right? I have x to the 1/2 on the top and a 1 on the bottom. And this is good because sums and differences we know work really nicely with derivatives, and so they work really nicely with antiderivatives too. And here I can just use the power rule here. I add 1 to the exponent and divide by that new exponent. And same thing here, I add 1 to that exponent and divide by that exponent. And I always remember to include the c. When I give tests on this, when I give you guys the test, many of you will occasionally forget the c. I give you one freebie. Right? So it happens to all of us, we forget the c. But if you do it twice, all of a sudden that becomes a pattern and you're going to get dinged for that, right? Not like a ton, but some, because it is important. If I don't put the c in there, I'm saying the antiderivative is this function, which is way more certainty than I actually know, right? Reality, I can only give you a class of functions, right, that look like this, but they could be plus or minus any value. And, you know, that makes sense, or should make sense, because remember, the derivative of capital F is this little f, right? That's the relationship there. And the derivative tells us all about the shape of the function. So I know what the function looks like, right? I know where it's increasing and decreasing, and I know where it's concave up and concave down. I mean, I haven't calculated those, but I can find all of that theoretically from this, the derivative. So I know, and I'm just, you know, I don't really know what it looks like here, but, well, it's not even defined for negative values. So, you know, don't don't take this literally, right? This is not actually a graph of f. But if I know where it's increasing and decreasing and concave up and concave down, that tells me it looks like this. But that same function could be right up here, right? Or right up here, or way down here, right? All of these functions have exactly the same shape in terms of the derivative. So knowing the derivative just tells me I have one of these functions. And what these are all the different functions plus some constant, right? The constant just shifts it up or down. So that's the reason that all those constants are important, because it's really telling us a class of functions. Questions about that introduction?